Our next speaker is Andreas Hauptmann, who's an assistant professor at the University of Oulu. And today his talk is entitled Networks for Nonlinear Diffusion. Thank you, Andreas.
Well, thank you for the introduction. And especially thank you for organizing that we can still meet here in this virtual mini-symposium. So what I'm talking about is actually research that work during my postdoc time at University College with Simon Erich. And actually nicely relating to the motivation that Stephanie gave, we are looking more into the conceptual part. So how to actually obtain, think about the network architectures and obtain new architectures or some more interpretable architectures. So you're wondering where Oulu is. Well, first of all, in Finland. Here you see a map of Finland, and actually we are pretty much in the north, so here. And if you're wondering as well, the Arctic Circle is actually here. So it's pretty bright at the moment. Okay, so let's jump to the actual scientific part. I'm starting here very abstract. So we are mainly interested in imaging applications, so basically image-to-image mappings. And we motivate this in a very broad sense. So we're interested in finding some sort of nonlinear mapping between two, let's say, functions, U and G. And we're asking the question, if we learn such a mapping, in which sense can these mappings actually replace physical models, or can we combine them with our knowledge of physical models? And what would be actually good architectures, and how can we interpret these learned parameters? So for instance, if we think about the most popular architectures, which, well, here based on convolutions, or well, in particular discrete convolutions, convolutions are sort of acting locally and are translation invariant. So a good question that we can ask is, are convolutions actually suited to represent a large class of physical problems? And could we actually improve interpretability or suitability of networks by considering other operations when designing these network architectures? And what we are following, well, you probably guessed it from the title, we're actually starting with diffusion processes, and we are for sure not the first one that look into that. And I just mentioned here two very important works that are very related to what we're doing. The first one by Chen, Yu, and Pock, which actually already looked into learning optimized reaction diffusion processes, so motivated by classical diffusion processes for image processing. They formulated a network architecture. And then recently published work by Rotorto and Haber on where they design network architectures motivated by partial differential equations. So this is basically my TLDR, very short, of that paper from PDE theory to resonant architectures, in particular CNNs. So what these works actually already provide us is insights into network architectures and the design, and in particular actually also in possibilities to constrain parameters. And so the question that we could ask now is what's left for us to do? And one thing that these two studies have in common, and please correct me if I'm wrong here, the filters that are learned there are still localized. So they're still very localized filters. So basically are still convolution-like. And that's also why it gives the nice connection to actually CNNs. But what we actually now consider in this talk is we want to design filters that are global, so spatially varying filters. And we follow pretty much the same motivation as these studies. So we start again from a classic diffusion, or in particular actually nonlinear diffusion process, discretize, and at the end we end up with a network architecture. So let's jump in. So, well, we have our classic diffusion equation, where now here it is important that our diffusivity, so nonlinear, depends on the function itself. And of course we have some kind of initial state, which could be either a noisy image or the image that we want to process. And in the following, we actually denote then the spatial derivative here by this L gamma applied to U. And here we actually make it clear that this gamma depends on U at each time instance. So it changes in time with the solution U. Okay, so let's look at two examples. Well, the simple, well, that's not nonlinear, but let's have first a look in the isotropic case. So if we have a constant diffusivity, simplified 1, then we actually just end up with the Laplacian as the differential operator, and we are, well, back to our classic heat equation. And here, actually, then the solution at time t is actually given by convolution with a Green's function, in particular, actually Gaussian. So here, actually, convolutions are a very good model. So that's clear. But if we move now to more general cases with nonlinear, in the nonlinear case, we're actually interested, as I said, on a diffusivity that depends on the solution U itself. And one classic example that I illustrate here is the so-called Perron-Harmonic filter function, where the diffusivity depends on the amplitude of the gradient. So that the motivation is here that we want to diffuse where the gradient is small, so that we actually remove noise, but we do not want to diffuse along the edges. So that's what we see nicely here. We actually, so here, if I stop this, we get a nice piecewise constant image. And here in the middle, we have the diffusivity that stops the diffusion along the edges. And what is clear, the diffusivity depends here on the solution itself. So it changes in time. Okay. So the problem is with these general nonlinear diffusion processes, there is of course no closed form solution here. And so we need to compute them numerically. And that's actually what we follow, very much the same motivation. Also actually what Stephanie nicely motivated to have a time-stepping scheme that is related to these ResNet architectures. So let's go back to our governing equation. And we can establish a connection between two time states. So now we denote the time state Tn. We have a realization at Tn, which is Un, and we go delta T forward in time. Then we can establish this connection between Un and Un plus 1 by integrating over our differential operator, which, of course, again, our gamma depends on the solution U itself. So this is, of course, we cannot solve this without knowing gamma, the diffusivity explicitly. So what we do is, or what one would do classically, you just fix gamma at time Tn and then approximate this integral by the length of the integral and just take one step. So now we fix diffusivity. And that already leads us to the general formulation of a time-stepping scheme. So this, well, previous leads directly to a formulation of an explicit scheme where Un plus 1, we call it now an operator, this operator that takes in gamma, acts on the function Un, which is the identity plus the length of our time step on the differential operator with fixed diffusivity. So this is very much related again to these ResNet architectures. Or what's also possible, we can also consider here an implicit scheme. So what's important or interesting to note is that this explicit scheme is only stable if these CFL conditions are satisfied. So we need small time step length, whereas these are unconditionally stable. But they're both only accurate if actually the time step goes to 0 in solving the PDE. So from this, we actually could already go forward to formulate the network architecture. So we would need to formulate this. But as some people might be familiar with my or Simon's work, we're from the inverse problems community. So we're also interested in actually the question to reverse this process. So we'll keep this in mind for the forward. And now we also go to the question of an inverse problem or the inverse diffusion. For simplicity, to have some the possibility to actually represent the functions, we consider now the isotropic case. So that means again for constant diffusivity. So we want to go from our time state ut back to the initial function. So then basically the inversion is a deconvolution process here with the isotropic diffusivity. And as we've seen, the forward model is a convolution, and we can represent convolution in space is equal to multiplication in Fourier space. So here we also can represent actually our function at time point t by multiplication in Fourier space. So this is now the Fourier transform of our Green's function. Then formally, so I really say here formally because this is numerically not possible, we could then go back to our initial state by, instead of here multiplying with this, by actually dividing our time point t. So this is now the division with this factor and taking the inverse Fourier transform. And of course, this is to be taken with a very large grain of salt. This factor is first of all unbounded, so there's no equivalent convolution kernel in the spatial domain, and also this process is unstable with presence of any noise and of course finite precision. So numerically that's not a viable approach, but nevertheless we will motivate from this formulation. We take now this factor in Fourier space, divide it into our n time steps. So we divide it into small time steps. Take this factor, expand it with the Taylor series. So then we have this formulation here, and take the inverse Fourier transform. So then we end up actually with this representation, again, in the spatial domain, which motivates the operator for the inversion process. So here, then we have this operator that actually takes the identity minus the time step and, well, our differential operator or here the Laplacian. And if we think about, if we remember, this term is actually exactly, so I go back 2 slides, it's exactly the inverse of our implicit time stepping. So this actually reverses our implicit scheme. So if we now plug this in, repeat it n times, take the time step to 0, and of course under any no presence of noise and infinite precision, we will converge to our initial solution for the isotropic case. In practice, this would be needed to be regularized, so we need some cutoff or thresholding, but nevertheless, we will take this operator as the motivation for the inversion process. So now we have the explicit time stepping for the forward and this operator for the inversion process. Okay. So from there, we can now move on to actually design the network architecture. So let's remind. So here we have the explicit time stepping scheme, which was the identity plus delta t on the differential operator. And well, very similar, as also Stephanie motivated, we now interpret each layer. So I write it as a capital U if it relates to the layer of our network as as one time instance of our function. And we want to now establish the connection between these layers by, well, so we write here this diffusion layer operator, which has the parameters gamma, which is the diffusivity, and the time step delta t, which are learnable, to establish this connection to the next layer. Okay. So, and of course, well, in practice, we need to actually discretize this. So here, in general, we consider now just a square image. We write for the discretized, we actually write this bold capital U. We have our explicit diffusion layer, and we would need to discretize now this differential operator. Where gamma here is now, as motivated at the beginning, it's global. So we have a spatially varying definition of gamma. So if we just take this as it is and discretize it, we get this. We get a stencil here, and I note that actually the stencil that we have here is mean-free, because it's a differential operator. We have it, we take it as mean-free, so we only learn these subdiagonals, which then define here our matrix that we would apply to the vectorized image. But you might already notice, if we define actually network architecture based on this, if we learn gamma, we actually, so here, we would need to learn a fixed gamma, which first of all depends actually on the image size. So that's not very practical. And it would not depend actually what our motivation was to find a gamma that depends on the solution itself. So if we learn this, this gamma explicitly, we lose this. But nevertheless, let's just formally, or let's just consider what we have. If we learn this gamma, plug it in this, we would learn sort of linear diffusion network. When we have our time state 0, we learn an explicit diffusivity, apply it to U0, add the identity on top, and then move forward in time with this scheme. But as just motivated, so this actually is not a nonlinear process because the gamma is fixed. So we want now for the nonlinear diffusion, and especially for the filtering, actually, we want that the filters or the diffusivity depend on U itself. So of course we cannot learn it explicitly. So rather what we need to do is actually find some implicit estimator. So that if we apply, let's just call it here lambda of some parameters, we apply this to our current layer, and that gives us then our diffusivity. And that can be then fed into our diffusion layer. So basically, we need some sort of estimation from the actual function that feeds it back to the diffusion or the differential operator. And in practice, well, we still use here very simple CNN. In practice, actually, we use a 4-layer CNN with 32 channels. So it's quite straightforward. On top of this implicit estimator, we also, as I'm motivated, want to do the inversion, where we had now for the inversion task, we had this inverse operator or the inverse filtering, which was given as the identity minus our differential operator. And on top, to make this stable, we would need to add some regularization. We have now here this inverse filtering part. We add on top a regularization and end up with a generalized filter. So we just absorb these two into one filter and end up with the identity minus this generalized filter matrix. We are still, again, we now call it W and zeta, not to overload the notation. And what's important here that actually, because these are now combined, so this would be mean-free, but with the regularization on top, that it doesn't have to be mean-free. So here, now we can also freely learn our the center diagonal on the matrix representation. And then, taking these two combined with the implicit estimator and this general filter function, we then end up with our nonlinear network architecture. So let's try to explain what's happening here. So we have again our initial state, which could be also in the inversion. It would actually be, then we start with UT and go back to U0. We apply our estimator, this lambda network, which feeds our filters into what we call a diffusion layer, which then this applies it to our U0. We add the identity and get to the next step, and we repeat it. So we first estimate, feed it back, apply it, plus identity, and then we move forward. So this, now actually the interesting part, what I want to point out here is the parameters that we learn are not zeta, so we don't learn zeta, but we learn this network. And we can also learn the time step delta t. So we only learn this actually implicit estimator in this context. So I also have an illustration actually in a moment to make this a bit clearer. Again, move to the basic problem of our isotropic diffusivity. So we take gamma to be equal to 1. So we have the basic deconvolution problem. Well, just for numerical reasons, we have 0 Neumann boundary conditions, and just take a time step to 1. And here's the illustration, quite simple. So here we have just some circular phantoms. We apply our kernel. So here we have also this illustration in Fourier space. We convolve the image, and then our network would give us the original image back. So to illustrate what the network is doing, so this is basically the architecture now of the actual images that are computed. We have the convolved image in the beginning. We have our simple estimator network that gives us here our subdiagonals. Now, shown this image, the center. Also note that actually the center has a different sign, which is fed back to this diffusion layer, applied to this one, and we get an update. So these are all added together, and then with the identity, we get to the next step. Here on the right, we nicely see actually what is happening. So we add here consecutively more of the higher frequencies in Fourier space. In the second step, same happens, or well, similar. We get our filters on the subdiagonals, apply it, get this update, and then we get our new state. And then at the end, so actually what we do is we let it free at the end and then apply just before the output, apply a cutoff, so maximum operator, the rectified limit unit to get our final reconstruction. Okay, so that was just for an illustration, what is happening in general. But well, as the title says, we're interested in nonlinear diffusion. So let's go back to this Malik filter, which is, well, it's a nonlinear diffusion process. And here in the following in the computational experiments, I'm concentrating on the inverse problem to restore the initial image from a diffused and noise contaminated image. For that, we use this SDL10 database because it has a nice amount of images, 100,000. We of course don't need the labels here. And divide it into 90,000 training samples and 10,000 test samples. We do not diffuse as heavily as shown in the beginning, so we only diffuse here a little that we actually can recover all the high frequency components. So here we see the original, and on the bottom there's a diffused image where the high frequency components are lost. And we, in particular, actually, we compare this to, well, one mostly out of the box network architecture, so-called DiffNet, which is a very large multi-scale network architecture. Let's say we were a bit disappointed. It performed very well. Of course, it always performs very well. But if you compare, so here that's not an inversion process without any added noise. That's the original image, and we are almost able to get a perfect reconstruction with our nonlinear diffusion network as well as with UNet, which is quite amazing actually from this diffused image. If we add noise, this of course doesn't work that well anymore. Now we add noise on top, 1% relative noise. If we compare now, I go back to the previous slide. If you look here at the high frequency components, it's clear that we can't recover them because they're just lost due to the noise contamination. But in the residuals, both networks perform actually pretty well. So now the question is, why do we do all of this? One thing, mainly what I like to point out is that the updates in this diffusion network are performed explicitly. So we can track throughout the processing what's happening to our image, which also, of course, gives us a natural way to incorporate constraints on the filters, the operator itself, or the time stepping. And so how we think about it is basically that this DiffNet learns more of a specific processing of the problem in contrast to a purely data-driven approach as the UNet, which needs a lot of data. In particular, so the network we used had only 5 layers with a 4-layer CNN for an implicit estimator, which ended up to be about 100,000 parameters. Compared to UNet, which has 34 million parameters, that's a considerable reduction in parameters to 0.3%. So, and we still get the same results. And actually this has also other implications because we need a lot less parameters. We have a more explicit processing. Also the amount of data that is needed reduces drastically. So if we look in the forward and inverse problem, so here this is the PSNR with respect to training samples. And we see that we kind of get plateau here at about 1,000 samples, whereas UNet just keeps increasing with more and more data, which is sort of expected. For the inverse problem, it looks a bit different, and these are a bit jumpy because we had a bit of problems with UNet and overfitting issues. So here we also see it plateaus, let's say quite early, when UNet, we get to the same reconstruction quality, but a bit more, and well, we actually had huge overfitting problems with UNet here. Okay, also one last point that I actually would like to raise is, so we motivated that we can decompose these generalized filters into actually this mean free part, which is the differential part, and the smoothing or the regularization. So, and it should, so the amplitude of this smoothing should increase with higher noise in our data. So that's what we postulate. And to get an estimate on that, we computed so an estimate of this regularization part by taking basically the mean free. We're taking the mean free part out of the filters, interpret this as our leftover regularization, and compute then the level of smoothing as the mean over the absolute values of S. And what we see nicely here is actually that this estimate of the amplitude of smoothing increases nicely with the noise level exponentially as we would expect. So this is one way to illustrate actually that we do get more interpretability of the learned filters that we actually have here. And that we were actually pretty happy to see this. So to conclude, so what I would like to motivate is that by taking the physics again into account, we get more expressive or suitable networks for specific applications. We can control and constrain the operations that are involved, and we get a very significant reduction in parameters and are having the possibility for some interpretability. What I actually wanted to hope to present in this mini-symposium was some work on experimental data. So if you're familiar with Simon's work, he's working a lot with diffusive optical imaging. Sadly, this is on hold. So maybe when we have this in person, this mini-symposium, hopefully I can show some results on that. Thank you.
Thank you for the great talk. Let's thank our speaker. We have time for also a quick question in the meantime while, let's see, Eric sets up his slides. Any questions from the audience? Wei has a question, actually.
Yes. Thank you, Andreas. It's an interesting talk. So my question is about the architecture part. So essentially the idea is to want to, at each step, you want to construct a bunch of filters. Of course, because you want to do nonlinear filters, so the filters are actually associated to the number of pixels, right? The number of filters.
So yes, if we would learn this explicit diffusivity, then it's fixed to the number of pixels. If we have this implicit estimator, which is here given as a CNN, it takes in the image and puts out an image. So it only learns to produce the filters from any image size. So that's nice. And actually in that way, it's flexible in the image size we apply it to.
Okay, so usually what you don't do explicitly, you learn directly. So you don't learn the filter itself, but instead just to learn the process.
Yes, yes, that's kind of the twist. So we don't learn actually the filters that we apply to the image that we process. We learn an estimator that gives us the filters that we apply to the image. So it's kind of it takes a while to get your head around it.
Thank you.
Thank you.
Well, let's thank our speaker again. Thank you. Our next speaker is